This is one instance of studying real numbers, okay, through axioms. So there you start with certain basic operations, and then you write down its axioms, and after that you actually proceed totally axiomatically. As if only those statements and this matter. What is a real number is not at all important. Okay? You can imagine all possible examples. Okay, tube, rings, fields, whatever. You can consider all possible. Okay, let me write down some of the axioms. Okay? For example, you say that this is associative. Okay? So you assume for all x, for all y, for all z, x plus y plus z equal to x plus y plus z. Then you may assume existence of inverse, for example. For all x, negation x equal to 0, x is not equal to 0, implies that this y, x dot y is equal to 1, and y is equal to 1. Okay? You may have a axiom for all x, for all x, for all y, x is greater than 0, since I have used less than, 0 is less than x and 0 is less than y, implies 0 is less than y. Okay? This is very typical of starting a mathematical theory. Whether you are doing natural numbers, whether you are doing real numbers or complex numbers, you try to write down certain starting concepts, write down certain axioms. And in the process, you are probably taking care of many other things. Okay? But whether I can, and then you really start reducing results from here. And as I told you, there are two ways of doing it. One is that you produce a proof starting from your axioms. Another is that you check in all possible models of real numbers, whatever they may be. Okay? For example, if you want to say something is a theorem of group theory, you say, look at all possible groups, and there you verify your statement is true. Only then you conclude a theory. But then, on the other hand, a philosopher's way is that, no. Whole reasoning rests on your notion of truth, and that follows certain logical principles, and everything is based on that. Okay? Now, I want to draw out the following thing. See, first of all, a statement that I could have said right in the beginning, but I didn't say. Beginning is done with syntax. Okay? And this is why, I have not explained to you that, why the adjective mathematical. Okay? It depends where you are doing the reasoning. Okay? A computer scientist, let's say a computer, when it is running a program, it is doing reasoning in one way. A mathematician is doing in another way. Okay? A linguist is doing a thing in another way. But what it depends, reasoning depends on how the sentences are formed, the structure of the sentences, as you can see here. Okay? There is a lot of relationship between this, on the structure of sentences, and also the principle of logic. Okay? So it depends. So your logic depends on two things. how sentences are formed. Okay. And two, the principles of logic that you are using, which vary from person to person. Principles of logic. Okay. And that is why there are variety of logic algorithms. Even for mathematicians, for example, there is something called propositional logic, there is something called first order logic, which depends on the way the sentences are formed, the class of sentences. In any case, in mathematical logic, so I am now working in the environment in which mathematics is done. Okay? And I have given you what mathematicians are doing. Whenever they are doing a reasoning, they have assumed certain acts. But before that, they have assumed certain undefined concepts. They start. So, depending on each theory, they have a certain symbols in the alphabet. Okay? So, these form part of the alphabet. And then, you know how the sentences are formed. I am not going to write down the precise definition of the sentence. Okay? Because from your practice, you know how formally sentences are written. Okay? So, just keep this broad idea in your mind. And this is the subject of mathematical logic. And then, I will tell you the reasoning done with this kind of sentence. Okay? Now, one thing that I should point out, that these quantifiers, they vary over the collection, the underlying set n, elements of m that matters. Okay? Which is a very, very important restriction. Quantifiers vary over elements of n. So n is, take any possible collection where you have defined addition, multiplication, you have fixed two constants. This. The quantifiers are only over your model, not over subsets of it. For instance, for example, one of the very important axioms for real number system is the completeness axiom or least upper bound axiom. Okay? So if you say every set of reals which has an upper bound, as a list of it will not exist. Okay? Here the quantification is over subset of reals. Okay? We are not allowed. So we are only illustrating through what is so these kind of sentences where the quantifiers only vary over elements of n are called first order sentences. Okay? This is an example of a second order sentence. Okay, so I am only restricting ourselves to the logic and to the logic done with first order sentences, and that is why it is called first order logic. And if you don't use quantifiers at all, only use negation or multiply, conjunction, implication, that's called propositional. But in any case, I am only considering first order sentences, so I am only giving you an overview of first order sentences. But this is extremely powerful. Okay? Now, assume a theory you have begun. So keep in your mind the theory. So you can write down certain axioms of real numbers and say that is the axiom you are starting. Now what do I mean by there are two meanings of some statement being can be proved or can be inferred from your axiom. One is that whenever these are true, okay, that particular statement is true. So that is one. Whenever they are true, whatever you want to do is true. Okay? Because you have done so many times this, for example, in group theory, when do you say something is a theorem? For example, if you want to say minus x is unique, okay, you will take any group and then you will prove that if y and y prime search for x plus y equal to 0, then using the axiom you verify that y equal to y prime. So one is that whenever your axioms are true, phi is true. Okay, for phi. On the other hand, I can write down few tautologies. Which by tautologies I mean something which is true by way of the logic that you are using. Okay? For instance, this one is true not because of any axiom. This one is true because of the logic that you have adopted. Okay? And we give the name to it logical axiom. So instead of calling tautology, we call it. These are axioms because of the logic. Okay? Now, what Gödel did is he listed down finitely many logical axioms. Of course, you should notice one thing, that there is a schema. For example, here, whatever may be the sentence say A and A implies B, you employ B. So it is not one axiom or one rule of inference. For each A implies B and B, this is an axiom. Okay? So for example, one of the logical axioms is what we call propositional axiom. You keep on using. Take any sentence here, either A is false or B is true. You use it. Okay? So this is a schema. Okay? It is not one axiom. But one more thing that you go on doing, because there are a lot of computer science people sitting here, it is mechanically possible to decide whether some formula is a propositional axiom. Okay, moment you see a formula, you can immediately see is it in this form or not. You can mechanically verify. Okay. Then another is, for example, contraction. No, contraction is a rule. So whatever it is, so for example here, modest contraction. 2 modest contraction. He wrote down 5 logical axioms. Let me see the number is correct. Okay, whatever, finitely many, 5 of them. And then we wrote down 5 rules of it. Okay, again some finite number. For example, 1 is, mod exponents is mod exponents is a rule of it. Instead of writing something in the form of for all, one axiom was substitution axiom. Okay? So one axiom was substitution axiom. For example, if something is true for a particular individual, we say there is X satisfied. Okay? And like this, he wrote down 5. Okay? Again, notice one thing, that I can mechanically verify whether a particular statement is deducible, it can be inferred using this rule from here, this rule. Okay? And then, you know what I mean by a proof. Huh? A proof is a finite sequence. Except that if you take any phi I, either it is an axiom, whether a logical axiom or an axiom of the theory, or can be inferred from previous ones using one of the rules. You can find this list, for example, in my book, such that for each 1 less than equal to I less than equal to phi I is either, well, the axiom special to the theory are called non-logical axioms. But that depends on what you are assuming. Okay? Whereas there are axioms which is true because of the logic. It's either an axiom, logical or non-logical. All can be inferred. From phi 1, phi 2, phi I. You will not need all. Using one of the rules. Okay? And what is great about it? That the two motions coincide. That if something is true in all the models, in every situation, you can produce a proof using only these finitely many logical principles. Okay? So, we will call it a proof of phi 1, phi 2, phi. Okay? This finite sequence, a proof of phi. Okay, the last step. And anything that has a proof is a theory. On the other hand, you have another notion that something is a theorem if it is true whenever the axioms are satisfied. Both are true. And that's the great theorem of Gödel. which is called Gödel's
সেটা কে বলছে?
complete
হ্যাঁ
principle.
সেটা কোথায় বলেছে এখন পর্যন্ত? সেটা তো একবারও বলেনি।
Completeness because he has given a complete set of logical axioms and rules of it, which is sufficient to do this step. To say that statement 5 is true whenever axioms of the theory are satisfied. If and only if it is a proof. In that sense. Okay? Okay. So now you can be a philosopher. I said what is written. Okay? In other words, are there certain principles of logic such that whatever else truth you determine, just follows based on it? And indeed the answer is yes. Okay? This was his doctoral thesis. Okay. Now let me start from here and try to see the value of it. I was saying that all these things can be more mechanically decided. Whether a statement is a propositional axiom or not can be mechanically decided. Whether B follows from A and A implies B, for instance, whether B follows using mod exponents can be mechanically decided. In other words, whether something is a truth or not can be decided by a computer. Okay? If only you can feed in the data. Okay? Well, this is where the artificial intelligence begins. It began with logic. Okay? So it can be mechanically decided. Now I cannot show much light. This is quite time consuming, but nonetheless, this is one thing that was exploited by Gödel. Gödel's interest was not in artificial intelligence and mechanizing things. He was in true sense a philosopher and a master, but he exploited it in proving his famous incompleteness. All that I want to say is that the germ of artificial intelligence, the first germ, took place in logic, in the world of logic. Okay. Let me now come back to some applications in mathematics. And I'm sure some of you may be waiting for me to state. This is not the most this is not the best result of Gödel. Gödel is very much famous for his incompleteness too. But that will come in passing. So let me give you some applications. And in that passing way, I will explain Gödel's incompleteness.